You forget a name, it's on the tip of your tongue, you know the person, you can see their face, but the specific set of sounds that makes up their name is gone. Where did it go? Is it still in your brain somewhere, just inaccessible, or has that little piece of information ceased to exist? This happens all the time. We lose keys, we misplace a book, we forget a password. On a small scale, information seems fragile. It feels easy to lose. We spend our lives trying to hold on to it. We write things down, we take pictures, we tell stories, we build libraries and servers to fight against this constant, gentle decay. Now, scale that up. Think about the Library of Alexandria, a vast collection of knowledge, of stories, of science. It burned. Most of that information is gone, not just misplaced, but gone. The specific arrangement of ink on papyrus that held those thoughts has turned to ash and smoke. The information has been scrambled into a chaotic, meaningless state, or so it seems. This question, what happens to information, isn't just about human memory or lost books. It's one of the deepest questions in physics. It pushes against the edges of what we know about reality. It asks about the nature of time, space, and the universe itself. The ultimate fate of information is tied to the ultimate fate of everything. To start, we have to agree on what information is. It's not just facts or data. In physics, information is a measure of specificity. It's the property that distinguishes one thing from another. Think of a coin. It can be heads or tails. That's one bit of information. The position of every particle in a gas, the sequence of every base pair in your DNA, the words in a specific order on this page, that's all information. It's the arrangement of matter and energy that makes the universe interesting. A perfectly uniform gray soup of particles contains very little information. Our complex, structured universe contains a staggering amount. The first clue to its fate comes from a grim cosmic rule. The second law of thermodynamics. It's a foundational concept in physics. It basically says that over time, in a closed system, things tend to get messier. The disorder increases. Physicists call this disorder entropy. A clean room will naturally become messy. A hot cup of coffee will cool down to room temperature. The heat, which was concentrated, spreads out. The order dissipates. This law seems to suggest that the ultimate fate of information is destruction. As the universe expands and cools, everything will eventually spread out. Stars will burn out. Matter will decay. All the complex structures we see today, galaxies, stars, planets, people, will fall apart. The universe will approach a state of maximum entropy, a cold, dark, uniform emptiness. The heat death of the universe. In that future, all the information that makes up our world would be scrambled. The novels of Tolstoy, the structure of a star, the memory of your first kiss, it would all be blended into a featureless, random static. The arrangements would be lost. From this perspective, the universe is like a cosmic Alexandria, and the fire is always burning, just very, very slowly. Information is temporary. It's a fleeting structure in a universe that favors chaos. For a long time, this was the prevailing view. It's intuitive. We see things fall apart every day. Why should the universe be any different? But then another area of physics came along and said, not so fast. That area was quantum mechanics. Quantum mechanics governs the world of the very small atoms and particles. And it has a very different rule about information. A core principle called unitarity states that information can never be created or destroyed. It can be rearranged. It can be scrambled. It can be hidden. But it can never, ever be erased from existence. Think of it like a deck of cards. You can shuffle them, you can deal them out, you can spread them across the floor. The order changes, but the cards are all still there. If you knew the exact position and velocity of every card as you shuffled, you could, in principle, reverse the shuffle and get back to the original order. The information is conserved. Quantum mechanics says the entire universe works this way. Every interaction, every collision, every reaction is like a perfect shuffle. The information about the initial state is always preserved in the final state, even if it's incredibly difficult to read. So now we have a conflict, a huge one, the biggest in modern physics. On one hand, thermodynamics and cosmology point towards a future where information is lost to increasing entropy. On the other, quantum mechanics insists that information is eternal. Which one is right? This isn't just an academic debate. It's a fight for the soul of physics. The ultimate battleground for this fight turned out to be the most extreme object in the universe, a black hole. A black hole is what's left when a massive star collapses under its own gravity. Its gravitational pull is so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. It's the universe's ultimate prison. In the 1970s, physicists like Jacob Bekenstein and Stephen Hawking started thinking seriously about black holes and information. A famous idea called the no-hair theorem stated that a black hole is incredibly simple. It can be described by just three properties: its mass, its electric charge, and its spin. That's it. It has no other features, no hair. This created a paradox. Imagine you have a book. That book is full of information. Now, you throw the book into a black hole, the book crosses the event horizon and is gone forever. The black hole's mass increases a tiny bit, but what happened to all the information in the book? The stories, the characters, the specific order of the words. According to the no-hair theorem, that information is just gone. The black hole doesn't remember what it ate. A book, a star, or a pile of garbage once they fall in. The black hole is the same. It only gets heavier. This is the black hole information paradox. It's a direct assault on the principles of quantum mechanics. If you can throw information into a black hole and have it disappear forever, then quantum mechanics is wrong. Information is not conserved. For a while, physicists thought there might be a way out. Maybe the information is still inside the black hole, just hidden from us. But then Stephen Hawking made a stunning discovery that made the problem even worse. Using the principles of quantum mechanics, he showed that black holes are not completely black. They glow very, very faintly. They emit a trickle of particles, now known as Hawking radiation. This radiation causes the black hole to lose mass over an immense period of time, trillions upon trillions of years, far longer than the current age of the universe. A black hole will completely evaporate, disappearing in a final puff of radiation. Here was the killer question. What about the information that fell in? When the black hole is gone, where is the information about the book you threw into it? Hawking's initial calculations showed that the radiation coming out was thermal. It was completely random. It contained no information about what had formed the black hole. His conclusion was shocking. The information was truly and utterly destroyed. This ignited a war among physicists that lasted for decades. Hawking, representing the world of gravity and general relativity, said information was lost. Others, like Gerard Hooft and Leonard Susskind, representing the world of quantum mechanics, said it was impossible. They argued that if information could be lost in a black hole, the entire foundation of physics would crumble, and the effects could happen without causes, that the past wouldn't determine the future. It was chaos. Susskind famously wrote that he and his colleagues would not stand by and watch quantum mechanics be burned at the stake. The debate was fierce. The stakes were nothing less than our understanding of reality. The problem is that you can't just say the information comes back out in the Hawking radiation. That radiation is created at the event horizon outside the black hole. The book, with all its information, is deep inside. How can the information get out? It can't travel faster than light to escape the black hole's gravity and imprint itself on the outgoing radiation. It's a seemingly impossible puzzle. Over the years, the tide began to turn. Physicists, wrestling with exotic ideas from string theory, came up with a potential solution. It's one of the most mind-bending concepts ever conceived, the holographic principle. The idea was first proposed by Gerard Hooft and later developed by Leonard Susskind. It suggests that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space. That sounds abstract. Let's make it simpler. Think of a hologram on your credit card. It's a two-dimensional flat surface, but when light shines on it, it produces a three-dimensional image. All the information needed to create that 3D image is encoded on the 2D surface. The holographic principle suggests that the universe might be like that. The three-dimensional reality we experience might be a projection of information stored on a two-dimensional surface at the cosmic horizon, the edge of the observable universe. It suggests that information is more fundamental than space itself. Space emerges from the information, not the other way around. How does this solve the black hole paradox? It redefines what falling in means. According to the holographic principle, when you throw the book at a black hole, its information never truly crosses the event horizon from an outside observer's point of view. Instead, the information gets stuck on the event horizon, which is the boundary of that region of space. It's scrambled and spread out across the horizon surface, like data on a giant spherical hard drive. From your perspective, falling in with the book, you would just cross the horizon and notice nothing special. But from the perspective of someone watching safely from a distance, the book's information gets plastered onto the horizon and thermalized. As the black hole evaporates via Hawking radiation, that information on the surface is slowly and subtly encoded into the outgoing particles. The shuffle is incredibly complex, but in principle, all the information that ever fell in is eventually returned to the universe. It's not lost, it's just released in a highly scrambled form. In 2004, after nearly 30 years of debate, Stephen Hawking publicly conceded. He announced that he had been wrong. He now believed that information was not lost in black holes. The details were still incredibly fuzzy, and they still are, but the consensus in physics had shifted. Quantum mechanics was saved. Information, it seems, is eternal. So what does this mean for the ultimate fate of information? It means the simple story of heat, death, and decay is incomplete. The universe may tend towards disorder, but it seems to be forbidden from erasing the information that defined its past. The universe has a memory. It might be a scrambled, hard-to-read memory, but it's a perfect one. The information about the Library of Alexandria isn't truly gone. When it burned, the information about the arrangement of ink on the scrolls was transferred to the arrangement of the ash particles, the smoke, the heat radiating away. To reconstruct the lost text from that scrambled mess would be practically impossible for us. It would require measuring the state of every particle involved and running the process backwards. But, according to physics, the information is still there. It's woven into the fabric of the cosmos. This leads to an even bigger idea. If information is fundamental and can't be destroyed, then what is the universe? Some physicists, like John Wheeler, have suggested that the universe is not made of particles or energy at its most basic level. No, it's made of information. His phrase for it was "it from bit." The idea is that it from every particle, every force, every piece of space-time derives its existence from information. If this is true, the universe is essentially a giant quantum computer. Everything that happens, from a star exploding to a thought forming in your brain, is a form of computation. The laws of physics are the algorithm. The state of the universe at any given moment is the data. And because information is conserved, this cosmic computation is reversible. The story of the universe isn't being erased as it goes along. It's being constantly rewritten and re-encoded. So what is the ultimate fate? It is not oblivion. It is transformation. The information that is an incredibly complex arrangement of atoms. Your body, your brain, your memories, when you die, that arrangement falls apart. Your body decomposes. The atoms that were you will scatter and become part of the soil, the air, a plant, another animal. The specific structure that was you is gone. But the information itself, the detailed description of that structure, it persists. It's passed on to the states of all the particles you interact with. The heat your body gives off, the sound of your voice vibrating in the air. Every interaction you have with the world leaves a tiny, indelible imprint. The universe records it all. As the universe ages and approaches its end, whether by heat death or some other scenario, all the complex structures will dissolve. But the information that described them will still exist, encoded in the subtle correlations between the remaining stray particles and photons wandering through the cold, dark void. It will be a universe that looks like random noise, but it will be a noise that contains the ghosts of every star, every planet, and every living being that ever existed. The ultimate fate of information, then, is to be eternally preserved in an ever-changing form. It's like a cosmic library where the books are never destroyed, but are constantly being shredded and reshredded, their fragments mixed together. All the stories are still there in their entirety, but they are distributed across billions upon billions of tiny, unreadable scraps of paper. This isn't a particularly comforting thought in a personal sense. It doesn't promise an afterlife for our consciousness. But it is a profound statement about the nature of reality. It means that nothing is ever truly forgotten by the universe. The past is not erased, it is embedded in the present. The arrangement of things might decay, but the information describing that arrangement is a permanent part of the cosmos. The ultimate fate of information is to become the universe's memory, a perfect, uneditable, and unimaginably complex record of everything that has ever happened. It is a story that cannot be unwritten. It is simply waiting, scrambled across the vast, dark canvas of space-time for a reader that can never exist. Or perhaps, the reading is not the point. The point is that the story is, and always will be, there.